Okay, limits and continuity. So, um, there's a lot of theoretical material that I'm going through to start with. You'll have to bear with me on that. The examples portion is set for the very end at these two parts, but I think it's useful to at least talk you through um, the the theoretical kind of way of thinking about limits to start with. So first let's recall how we defined limits back in Calc 1. So remember that this symbol was actually a two-sided limit. And it only existed if the two one-sided limits were equal to each other. So if the two one-sided limits are equal, the left and the right, if they're equal, then you end up defining the two-sided limit to be that common value. And so this gets generalized to Calc 3 in the following way. So these two directions were actually the only directions to approach the point A on the number line, right? On this one-dimensional um, space that we are working within. But in Calc 3, we're dealing with functions that have two variables or maybe more, but we're going to try to restrict ourselves to just two dimensions in this case. So in two dimensions, well, you see that you got a point in two-dimensional space. There's a lot more than two different ways to approach this point. Um, and so the definition for limit is going to generalize the idea of approaching that point in whichever direction, and no matter which direction, uh, if the function gives you the same value, then that common value is defined to be the limit. Right? The limit should be independent of what direction you approach the function in. So no matter which direction, it should be the same value. And I guess an important comment here is that so all possible directions does not just mean all possible linear uh, directions. You actually need to consider every possible curve that passes through, which is way more than just the linear paths. And we'll see an example that showcases that just considering lines approaching the point is not enough. Okay. Um, I this section you can actually pretty much skip, but I'm gonna talk through it a little bit because the book does, and I didn't it didn't feel right for me to completely exclude it. So this is the abstract way of defining what we mean to approach in every direction. So the issue is that this every direction is difficult to capture. It was easy in Calc 1 because you only have two possible directions of travel. But once we have more than one dimension, we have to actually start talking about this idea of closeness involving these disks of a particular radius. So delta and epsilon are supposed to be small quantities, real numbers that are less than 1. And, well, a delta is supposed to stand in for the radius that you're talking about. So, really, it could be a delta disk, an epsilon disk, but that symbol is representing the radius of the disk. You can see that in this formula here. This is the formula of a disk centered at the point A comma B with radius delta, which is the picture I've drawn here. So, um, not including the boundary of the disk because this is a strict inequality, right? We don't have an equals there. Okay, right. And so then the definition of this is the formal mathematical definition of um, the limit of a function as you approach a point. So it's the limit of a function is equal to L if you have this complicated paragraph. For every epsilon, there exists a delta such that all points in a delta disk around um, the, the target point A comma B, the value of f of xy is no more than epsilon away from the value L. So yeah, symbolically it's like this, and I guess let me just try to impart the intuition here. So it's saying that if you are with how do I want to say it? For any epsilon, there is a particular delta down here that guarantees that when you take any point within delta away from the point A comma B, you send it through the function f, you'll land within epsilon of the limit. This is a way of expressing closeness. You want it so that as you kind of shrink yourself towards the point A comma B, that you are controlling how close you are to the value L. So that as epsilon gets smaller and smaller, as delta gets smaller and smaller, epsilon will get smaller and smaller. Although we kind of invert it the other way. We invert it so that to make it into more of like a question and answer process of like, say I want to be within 0.1 of the target L. Well, I can find a delta so that I can be within 0.1 of L, and then 0.01, and then 0.001. And if I can always do that, that means that I have guarantees on getting arbitrarily close to L. That is what it means, very rigorously speaking, to say that the limit of the function as you approach the point A comma B is equal to L. It's this idea of shrink wrapping towards the point A comma B, you get arbitrarily close to L. And I should just say that, yeah, this definition is only something you need to work with if you're a math major and you take a course called Real Analysis. You don't need this for Calc 3. I don't know. I think all books do kind of hand wave this. All calculus books kind of hand wave this, saying, like, this is the rigorous way of doing it, but you're not expected to understand it as a calculus student. So it's very much okay if you don't. All right, let's continue on and talk about continuity. So, right, this is something you should kind of recall. Right, so in Calc 1, continuity was defined in this way. I normally just point to this expression, and so when I teach Calc 1, I sort of write it as this expression, but then I tell my students that this expression actually says three different things. It says that the left side exists, the right side exists, and that these two expressions are equal. So let's unpack what that means. So a function f is continuous at the point x equals a. If f of a exists, that means that a is in the domain of the function f. You can actually plug a into the function and you get back some value. Right, so that's the first part. The second part is saying this two-sided limit, right? Back in Calc 1, this was a two-sided limit, meaning that the two one-sided limits were equal to each other. So this limit existed as well, and that these two things were equal to each other. So this is an instance where they're not equal, and this is what you're trying to avoid in this definition. You're trying to get rid of this very last type of discontinuity, this what I call a point discontinuity. I know that it's commonly called a removable discontinuity, but yeah, this is the instance where the two-sided limit exists, and the f is defined at a, but they're not equal to each other. Right? That would be a removable discontinuity. You don't want that. You want instead this point is at this gap, right? And so that is what would define the function being continuous at the point A. That was your Calc 1 definition of continuity at a point. And the idea is that this extends directly to functions of two variables and higher. So functions of two variables, it's exactly the same thing. You have that it's that the point is in the domain of the function you're speaking of. So plugging it in, the value exists. It's that the limit as you approach that point exists. Now this means a bit more in Calc 3, because this means not just two directions, but every possible direction that you can approach the point A, comma B. It has to, the limit has to be the same quantity in order for this limit, this two-dimensional limit, to exist. Okay? And then lastly, that these two quantities have to be equal to each other in order for the function to be continuous at that point. And again, this is to get rid of the possible point discontinuity that can occur. Okay. And well, these properties are just, they're things that you would expect for continuous functions to satisfy. So it's just good to note that yes, they do satisfy them, and we don't really have to go further into that. So sum of continuous functions is continuous, product of continuous functions is continuous, and composition of continuous functions is continuous. It's nice properties that you would hope or you'd expect to hold true. They do hold true. Okay. Limit laws are also things that you pretty much would expect. So, and these basically carry over from Calc 1. So, if we let the limit, so in all these below statements, the limit is approaching the same point, a comma b. The function f approaches the value L. The function g approaches the value m. C is some constant. Okay. Then, limit of a constant is a constant. Limit of x and y end up being the values that you're approaching. So the x-coordinate approaches a, then this limit of x approaches a. Limit of y approaches b. Sum and difference. So if you're taking the limit of a sum or difference of two things, you can split the limit over each of the terms and take those limits individually. That's what this is saying. You can pull scalars out of limits. So these two together mean that limit is a linear operator, which is the same as what you know holds true in the one-dimensional case in Calc 1. Product and quotient of limits, or of functions. So yeah, the limit splits over product of functions, it splits over quotient of functions, and the power and root law. So these, the way I think about these is that you can pass limit through continuous functions. You can pass it through the square root function, or the square, the power function is what I should be saying. The power function in this case, and the root function in this case. You can pass limit through it, take the limit of the inner function. Okay. So those are all properties that we pretty much expect. So that's pretty good. Now for the main, I guess, the main aspects of this topic of how do we actually take limits. So in good situations, we are able to rely on just basically plugging things in. So in these two examples, you can actually resolve them by just plugging things in, and this is what I'm classifying as good behavior, where the function, where the limit works nicely, where it exists basically. So, so in this case, as you can see, you can just directly plug in and get nothing problematic to occur. So this should always be the first thing that you try to do. You should always try to plug in first, and if there aren't any issues, then that's great. Just like I think as you're used to doing with limits. The next one here, when you plug in, you'll notice that you get 0 over 0. but this actually has an algebraic simplification, which is similar to your exercise. So with this one, if you factor the top and bottom, you can see that you get this cancellation. And this cancellation gets rid of the singularity, the 0 over 0 that is occurring. So the resulting rational function you can just plug into, and you get a sensible value out of it. So yeah, doing this type of problem was as you would expect, I think. Well, it's analogous to the types of problems that you've dealt with in the one-dimensional case, where you massage your limit by using algebraic techniques to rework it. And now this is kind of the part that is more problematic about these limits in higher dimensions. So if you don't have a case like these previous two, then what you probably should try to do is to see if there are different directions that you can approach the value from, which end up giving you different results. Because once you have that two different directions give you two different results, that means that the limit does not exist. Right? It cannot exist. One important thing that I need to stress about this is this technique or this process can never be used to show that the limit exists. It can only be used to show that the limit doesn't exist, right? Because in order for the limit to exist, you need some argument where, regardless of what path of travel you take, the limit will always give you the same value. That is a really difficult statement to make happen because we're talking about every possible path. That's a very large infinity of possible paths. And in fact, there is technically a way of doing that. It's a different technique. It involves converting your limit over to a limit in polar, and then once you've converted that limit into polar, you would be taking the limit as r goes to 0, and then you need that the function is independent of theta, and it's only dependent on r. If you end up having that property, then taking the limit as r goes to 0, that conversion is equivalent to saying that no matter what path you take, the function ends up approaching the same value. So this conversion to polar, it is a technique that has been taught in other renditions of this class. I don't know if it's going to show up for us, say on the test. We'll find out, I guess. But yeah, I'm not going to linger on that. I don't even have an example about that. I just wanted to mention that is a technique that is out there, but it's not something that I've written here. So it's one thing to be aware of. That is a way to show a limit exists, and it is quite a powerful technique. But we have this instead, where we're considering different paths. Considering the specific different paths can never be used to show that a limit exists, only to show that it doesn't exist. Okay, let's come back to this example. So in this example, you see that if you just naively plug in, you'll get 0 over 0. So that doesn't give us anything. Instead, we need to try something else out. And you can kind of tell that there's not really any algebra you can do to simplify this to like in the previous example of like algebraic simplification. There's none of that. So instead, we sort of try out different paths and see if different paths will give us anything. So first, the easiest paths to start off with are the paths where you have one of the where you set one of the coordinates equal and you approach along the other coordinate. So in this case, because we're approaching the point 0, comma 0, we would set x to 0 or set y to 0 and approach along the other direction. So pictorially, it's like this picture. So saying approaching along the line y equals 0 would be approaching along the x-axis, approaching along this one. And so that's the first thing that we can consider. If we do that, notice that we just would plug this kind of specifying this direction of travel ends up simplifying our limit. We can substitute things in for our limit. So setting y equal to 0 in our limit, we would get 0 on top, and we would get 3x squared plus 0, which simplifies down to this. And then the only thing that varies, since we've set y equal to 0, x is the only thing that varies. We let x approach 0, and this reduces our limit down by a dimension, so that it's something we're more comfortable with working with, I suppose. And you can see right away that like this is equal to 0. Okay, next you could approach along this other line, approach along x equals 0, so that's along the y-axis. I could have drawn it the other way as well, but I like to approach along the positive axes. So when you do that kind of simplification again, so you set x equal to 0 and replace it in the function to kind of simplify the limit, you end up with 0 on top and then y squared on the bottom, which is whatever in here. So the limit simplifies to this, which you can clearly see it equals 0 as well. Okay, so that hasn't given us a contradiction yet. So let's try a different path. Now, if we try the path, the next easiest path would be a line y equals x. And this does give us a problem. So if we approach along this line, which is the line I've depicted in red, you'll see that what I do is I replace y with x in the expression. So I get 2x squared on top, and I get 3x squared plus x squared. I get 4x squared on the bottom. And we let x approach 0. We can see that this simplifies to give you 1/2. And 1/2 is not equal to 0. So we found two different paths of approaching the point 0, 0 that resulted in different values. And so the limit does not exist because we found two possible, two conflicting values. Okay. This last example is a pretty key example, I guess. Pretty standard as well. So the fact that not all considering all lines is insufficient. So this is an example of a limit where you can approach the point along all possible lines and you get a consistent answer, but there is a curve where you don't get the same value, and so the limit does not exist. So you can quickly check that if you approach along the x and y axes, you're going to get 0. So approaching along these axes, you get 0 on top, and you get one of these two terms in the denominator. So the limit simplifies to 0 over a non-zero value, which is equal to 0. Okay. If you approach along the line y equals kx, so that's going to give you every other line that passes through the origin. So if you consider this expression, then what I do next is I plug in for y the value, the expression kx, and I simplify that, and then I factor out an x squared and I cancel. So I cancel out x squared top and bottom, which gives you this, and then at this stage you can plug in 0, so you end up with just a 1 in the denominator, 0 on top, so you end up with 0. Okay, so all possible lines through the origin, the limit was 0. But if we choose this particular path, x is equal to y squared, then plugging that into here, so you see that you get a y squared on top and a y to the 4th on the bottom, right? Then this ends up simplifying to give you the value 1 for the limit. And so that is a different value. So this curve shows you that the limit doesn't exist. And again, I want to stress that this technique, or this method of choosing different paths and trying them out, can never be used to show a limit does exist. It only can be used to show a limit does not exist. Right? To show a limit does exist, you would need to make an argument about how every single path would give you the same value. And you can't possibly enumerate through every possible path. That's not possible. There's way too many possible paths. Instead, there is this other technique involving polar, but I'm not going to go into that unless we actually end up needing it. Okay, well, I guess that's it.